All right, today we're going to talk about chapter 15. We're going to talk about the general multiplication rule. This is D33, and the general multiplication rule and independence. So in the last chapter, chapter 14, we learned the probability rule for finding the probability of A and B when A and B are independent. And that rule was the probability of A and B, and remember the other notation, the probability of A intersect B, that's the same as A and B, is equal to the probability of A times the probability of B. However, now that we understand a little bit about conditional probability, we can use the general multiplication rule, which works whether or not the events are independent. So we've got the probability of A and B is now defined as the probability of A times the probability of event B, notice it's the same as up here, given that A has already happened. And this would work whether the events are independent or not independent. So this rule comes directly from the conditional probability formula we learned yesterday, which was the probability of event B, given that A has happened. If I were to write that, it would be equal to the probability of both A and B happening divided by the probability of the given one, which would be the probability of event A. So if you simply take this formula and rearrange it so the probability of A and B is by itself using rules from algebra, so to get rid of dividing by the probability of A, you multiply both sides of this equation by the probability of event A happening. Then what you end up with is the probability of the probability of A and B is then equal to the probability of A times the probability of B given that A has happened. So it's just rearranging that conditional probability rule from yesterday. So let's take a look at an example of using this. So what is the probability of drawing two aces in a row from a deck without replacement? So two aces in a row would be the probability of getting an ace times the probability of getting an ace given that you already got one ace. So two aces in a row means the probability of getting an ace and an ace. Okay, that's generally what that means, which then actually means since it's an and probability, you multiply the probabilities. But since drawing the second ace is not independent of the first, it's the probability of drawing an ace the second time, given that you already got an ace in the first draw. So the probability of getting an ace from the first ace would be 4 out of 52, times the probability of getting the second ace knowing you've already got an ace in your hand would be 3 out of 51. And then you could just multiply those together, just get it as a decimal, 4 divided by 52 times 3 divided by 51, and that is 0.0045. All right, so now suppose that 23% of East High students are seniors and that 65% of seniors are taking a math class. What is the probability that a randomly selected student is a senior and taking a math class? So we're looking for the probability that they are a senior and they're taking a math class. So that would be the probability that they are a senior times the probability that they are taking a math class given that they are a senior. So the probability that they are a senior from the information is 23%, 0.23, times the probability that they are taking a math class given that they are a senior is 0.65. So we just multiply those two and we get that the probability is 0.1495. All right, so now we're going to look at a situation where we have 12 girls on a softball team. 6 of them are freshmen, 4 are sophomores, and 2 are juniors. So we're going to select 2 players at random, and this is going to apply to all of these parts of the problem. So I'm going to select 2 players at random. This is going to mean that I'm going to have and probabilities or probabilities every time, most likely and probabilities. Further, okay, so these, selecting 2 at random, you're going to have and probabilities. And you're also going to have probabilities the events are not independent. Okay, so general multiplication rule is what we're going to use. So what is the probability that both are juniors? So the probability that you get a junior and a junior would be the probability that you get a junior first times the probability that you get a junior second, given that you already got a junior first. So that's actually that's what we're going to calculate. So the probability that you get a junior first out of the 12 is, because you have 12 people to pick from to start with, would be 2, times now a probability that you got a junior on the second time, given that the first one was already a junior. So now there's 11 people left and only 1 junior left. So that is what you're going to multiply. And you get that probability is 0.0152. All right, so neither is a junior. So that kind of translates into the probability of not a junior and not a junior. Remember, another way to write that would be the probability of J complement and J complement. Complement means not a junior, okay? So that would mean the probability of getting J complement on the first time you chose somebody times the probability that you get a J complement, not a junior, given that you already have one person who's not a junior the first time. So so the first junior that you pick the first person that you pick is not going to be a junior. So out of the 12, how many are not juniors? That would be 10 of them. Okay, now you've already picked someone who's not a junior, so now the probability of getting a junior on your second person, given that you already got a junior on your first person, is 9 out of 11 now. So then you're going to take 10 divided by 12 times 9 divided by 11, and you're going to get that probability would be 0.6818. All right, so now at least, here's that at least probability again. It was in the last videos too. So at least 1 is a junior would be the probability that greater than or equal to 1 is a junior. So the way we always handle that at least would be the complement. 1 minus the probability that none or neither of the two, none are juniors. Okay, so the probability of at least 1 being a junior means the probability is, or the probability that greater than or equal to 1 of the 2 is a junior. So that would kind of mean 1's a junior and 1 could be a freshman. 1's a junior, 1 could be a sophomore. So we don't want to look at all those possibilities. In fact, we don't even know how. The way you always handle an at least probability is you take 1 minus the probability of the complement of this. So the probability at least 1 is a junior is none are juniors. So we already figured none are juniors in the last problem. So this would just be 1 minus 0.6818. So that would be 0.3182. All right, so now the last one, all of them are from the same grade. Okay, well, all of them being from the same grade, well, let's see, that would mean that the probability that both freshmen or both sophomores or both juniors. So what that actually means is the probability that you get a freshman first times the probability that you get a freshman, given that you already have a freshman, that's for this probability, plus, because or probabilities are added, the probability that you get a sophomore first and a sophomore second, given that you already got a sophomore. So that's the probability of getting both sophomores, plus, that's an or, the probability of getting a junior times the probability of getting a junior the second time, given that you already got one first. So the probability of getting a freshman on the first draw would be 6 out of 12, but the second time is only 5 out of 11. Plus the probability of getting a sophomore would be 4 out of 12, times the probability of getting a sophomore second would be 3 out of 11. Plus the probability of getting a junior first would be 2 out of 12, times a junior second is 1 out of 11. So now we're just going to take 6 divided by 12 times 5 divided by 11 plus 4 divided by 12 times 3 divided by 11 plus 2 divided by 12 times 1 divided by 11. And we get not the right probability here. So, all right, so finally I guess I got it right. 0.3 repeating is basically what it is, 1/3. You could go through and you could like reduce, and that would be 1 and that would be 2, and so this would be 5 over 22. And then 4 would go into 12 3 times, then 3's cancel, so plus 1 over 11. And then this one, the 2 would be 1, 12 would be 6, so this would be plus 1 over 66. When you combine all those, you do end up getting 0.3 repeating. So, when sampling without replacement, successive selections are not independent. When the population size is known, you should adjust the probabilities accordingly. That's what we did when we reduced the bottom by 1 each time. All right, so let's just take a look at an example here. Following shows the relationship between a grade and having a driver's license. So we want to look at this problem here, and we want to answer some questions. So the questions we want to answer, we're going to select a student at random, and I want to know what's the probability that he or she is a freshman. Okay, so the probability that he or she is a freshman, basically, if you total all these up, this is 0.27, this would be 0.25, this would be 0.25, and this would be 0.23. If you add all of these totals up along the bottom here, you end up with 100% or 1. So these are all given as percents. So like if you add these up across here, 0.27, 0.28, 0.33, and then this one has to be 0.67. All right, so basically we actually have all the probabilities here. So the probability that they are a freshman, here's all the freshmen. Okay, so this is the 9th total down here. Okay, so that would be 0.27. So now part 2, I want to find the probability that they have a license. Okay, so that probability, how many have a license? So that's 0.33. So that's the have a license total. All right, so number 3, what is the probability that he or she is a senior and has a driver's license? So now I'm going to look at a row and a column. So senior and has a driver's license, that would be 0.16. All right, number 4, what is the probability that a senior has a driver's license? So senior has license. So that means the probability that they have a license given that they are a senior. That's what that means. So I'm going to look at the seniors. So this is going to be out of 0.23. Out of 0.23. Okay. Because we've narrowed it down to the seniors, we know they're a senior. How many have a license? 0.16. So we're going to take 0.16 divided by 0.23, and that's going to give me 0.6957 for our percent. All right, I'll finish this on the next video.